Okay, so let me give you a second characterization of differentiability. So say I had a function, f of x and y, and I wanted to define kind of is differentiable. Maybe let me call this object a definition. This is not actually a definition. This is kind of a theorem. So f of x and y is differentiable at a point a, b if fx and fy exist at a, b. Sorry. Does that seem like a reasonable condition?
Yes.
Yeah.
Like, if I'm going to say something's differentiable, I should be able to take derivatives, right? Okay. So if they exist at AB, and if fx and fy are continuous in some disk around AB. Now that is well pathological, right? So I've been telling you guys that differentiability really means that there's a local linearization, right? To get a local linearization, really all I need is this first bit, right? I need just fx and fy to exist at AB, and for it to make sense for me to plug AB in there, right? Okay, so this thing is just a touch stronger, right? So this is saying, well, I lied to you a little bit by saying that a local linearization was enough, right? But in what case have I lied to you? Like, in other words, what would it look like if a function met this, didn't meet this last part, but did have that local linearization?
It was just like a point that was separate from the rest of the function.
Yeah, like somehow one of these derivatives would exist at a point, but not be continuous there, right?
So like the point at the bottom of the parabola, maybe?
No, I mean, even
It's
that's...
like, it's like one of those functions that say like, it's y equals 1 over x for x does not equal 0, and then at x equals 0 equals 1.
Yeah, you probably want some kind of piecewise function. It would need to actually be differentiable, which is a bit of an ask, right? You guys see that?
Yeah.
But it needs to be continuous only at one point. So something you could do to make some kind of pathological thing like this is you could make, and I'm just doing this in one dimension, just for illustration. We could do a function of x that, let's see, we'll make it x squared if x is in the reals, less q. Right? So take all the rational numbers, right, the fractions out of R, toss those aside. This thing is x squared on the irrational. You guys see that?
Q is the rationals.
Q is the rational. Q stands for quotient. Not like Z, which stands for something in German.
What does that lowercase e mean again?
Oh, if x is in.
Oh, okay.
So maybe let me write this out nicely. If x is irrational, so that I'm not confusing you with notation as well as a really weird example. And let me say f of x is minus x squared if x is rational.
So that the graph of that would be.
Okay, so the graph of that would be.
Oh.
Okay, so sometimes it's x squared, right? So sometimes it looks like this. And other times it looks like
That thing flipped over on the part that's not so.
sometimes it looks like that.
Oh.
And the times that it looks like this, it doesn't look like that. And the times it looks like this, it doesn't look like that. That's cool.
So
this is just specs, right?
so
Now there are a bunch more specs on the which side? You guys know this?
On negative x squared.
Yeah, there's way more irrationals than there are rationals. So the x squared line, right, this guy, is like most of the things. And then there are lots of things down there, but many less of them.
So mostly dots and then a couple of dashes.
Yeah, so mostly this is hard, right? And then this is a little bit sparser. Keep in mind that when I say sparser, I am fully lying to you. Because if you pick any little guy like this, right?
They're both infinite, like you can't tell.
There's infinitely many points that end up there and infinitely many points that end up down here.
Is there an infinite number of rational numbers within any interval?
Yeah,
Yeah.
and they're dense. So if you pick any little interval, like if you divide this thing in half, it's still true that there are infinitely many of both in each side. If you cut this down all the way, right, you will not be able to find a pair of these for which one of those isn't in the middle. And you won't be able to find a pair of these for which one of those isn't in the middle. Right? You guys see that? So there's dust and it's thick here, right? Now, if I ask about drawing a tangent line to this thing, you guys see that? The squeeze theorem will tell me that I can draw a tangent line through the middle there that's horizontal. Yeah, so isn't there an issue with continuity at 0, right? No. The limits from both sides work, right? They're equal, and they are the function value there. So to get continuity, there's the continuity triangle. Do you guys know this thing? Maybe not?
Yeah.
Okay, so let me throw that at you. So the continuity triangle says f of x is continuous at x is a if the limit x tending to a from the negative is the limit x tending to a from the positive, of f of x, I suppose. And both of those things, right, have to be equal to f at a. This is the continuity triangle. Those two things have to be equal, and they have to equal the function value there. That's cool?
Okay,
Oh, yeah.
So, the limit as x goes to 0 from the negative of this thing is 0. You guys see that?
Is 0 rational or irrational?
0 is rational, because you write it as the fraction 0 over 1.
Okay.
From the right-hand side, that limit is also 0. And we just said that f of 0 is 0. Right? So it's continuous there. It's not continuous anywhere else. Yeah, so there's only one value of continuity. If you fiddle around with the squeeze theorem, you can get a derivative out of this thing. It's only differentiable at the one point that it's continuous at. You guys see that? If you constructed a two-dimensional analog of this thing by like adding a y coordinate, by just saying comma y, right? You would get one of these things where a local linearization, right, like a tangent plane is constructible, but there's some problems with continuity, right? That said, how often are you going to run across one of these things? Depends. If you're a mathematician, maybe fairly often. If you're an engineer, never. You guys cool with this? Like, it takes something really, really messy and pathological to have a derivative at one point and not be continuous in some little neighborhood. It's possible, but not likely. You guys cool with that? So we could construct a local linearization for that, but it's still not actually differentiable. Your book gives a different criteria for differentiability. Do you guys want to see it while we're talking? Okay. So a different criteria for differentiability would be that you want the error to go to 0. Right, and that's the problem with this thing. The error doesn't go to, yeah. It is. So we could construct some kind of a error function, right? How do we make an error function?
Use the Lagrange error function if you wanted to.
What's that?
You can use the Lagrange error function.
No, let's use an easier error function. Let's just think about what the error is, right? The error should be where you ought to be minus your approximation, right? Okay? So if I take the error, that should be this. And what do I want? I want the limit as x and y tend to a and b, right, of my error function divided by, I don't want percentage error. So I want absolute error here. I want to divide by how far away I am. Does that make sense? Like this result should be, this should be like the second order approximation and higher stuff, right? So if this linearization is good, I should be able to divide out one of this kind of distant, maybe let me just write this as a distance. So distance from x comma y to a comma b, right? So I'm really thinking this guy should be second order. And when I divide by this distance, that's like first order, right? So this thing should still be first order. And I'm sending x and y to AB. So this should end up at 0. You guys see that? You take a second order polynomial, you divide by a first order polynomial, it should still have first order. And that should go to 0. You guys see that? I may have lied to you about the earlier thing. I may have lied in that this thing that I made a second ago, this might still be differentiable. The error might still go to 0. It would be something like this to make a non-differentiable function. Right? I said the linearization for this exists and I could make it, but it doesn't satisfy this thing. Well, under this criteria, it might still work. You guys cool with this? So this would be another thought I could use. If you go fiddle with the Calc 1, like write down a second order Taylor, right, just write down a second order polynomial, subtract the linearization at a point, and see that this still happens. It might be enlightening to see that second order divided by first order makes something that still has first order terms. What's up, Sally?
I was wondering how you determine there's more rational or more irrational than rational.
Oh, that's a really cool question. Let's ask that one instead.